קו 17. הוא בכלל בפונקציה.
ואני אספר לכם בינתיים, מי שאל אותי, אתה שאלת אותי כמובן, על, so okay, I've done 2 anyway, so I'm reminded that last time we proved that A star A for any element in the C star algebra is always positive, and I said that I mentioned that this result is was open for several years. So I read a story. There is a nice paper of Cadison. So Cadison was sister algebraist, operator algebraist. He's the advisor of Bill Alverson. Sorry.
He's your great-grandfather.
No, he's my yes, the advisor of Baruch Sorel, which is the advisor of my advisor. Okay, no, what I wanted to say that he wrote a nice note like 50 years after the GNS was published. GNS is the main theorem, which we're going to see next time. And there was a nice journal called 50 Years for Sister Algebras, like thing. And then he gave a little bit history background about the original definition of sister algebras and everything. And indeed, in the original paper of Gelfand and Naimark, they defined, they didn't call it sister algebra, they called it normed ring. And the normed ring was a Banach space, A, satisfying the Banach inequality, something that is similar to the sister inequality, and this additional assumption. Well, it wasn't that A star A is greater than 0. The assumption was that 1 plus A star A is invertible. So this was one of the assumptions in the original paper of Gelfand and Naimark. In particular, if A star A is positive, then clearly this is invertible, right? Because the spectrum does not contain, is bounded away from 0. So they assumed this, and they wrote in their original paper, we believe that this is redundant, that we can omit this assumption. Yes. So it took more than 10 years until Kaplansky came and removed this conjecture, this assumption. And his proof is exactly the proof I gave you last week. So it was really cool. So now I want to continue a little bit with positive elements. And then we're going to take a pause of sister algebras because I will need a few facts about, briefly facts about phenomenon algebras. So just a few things we will do there and immediately go back. So last time we finished by showing this is positive. And of course, every positive element is of this form. So this is something we knew before. And now a few things I wanted to add last time, but I didn't have time. Claim if A is positive and X is any element, then X star AX is positive. So why is this true? You see it? So X star AX is clearly right, it is A to the half X star A to the half. Claim if A and B are positive and A is less than B, then also X star A X is greater than X star B sorry, is less than star b x. And well, this is fair because we might say something. And and lemma. By the way, I have written. I mean, I'm in the middle of writing. I think I will finish it tomorrow. And exercise. Some questions about sister algebras. The last two, you will have to wait a little bit to be able to solve them, maybe like a week or so. And yes, and one of the questions will be show that if a is less than b, then the square root of a is less than the square root. But another question is that if a is less than b, it might be the case that a square is not less than b. Anyway, lemma, so it happens also for taking the inverse. So if a is greater than 0, then b inverse is greater than a. So you can think of it as if the function. So okay, so there's in fact a notion here which is more general about monotone functions on sister algebras. In fact, here I'm just saying that the function -1/x is monotone when you think of it over sister algebras. And I also said before that square root of x is such a function, but x squared is not. I mean, even on positive levels. So, but this is okay. You can read it more about monotone functions if you want to, about Pareto monotone functions.
Is it easier to see for square root of x than alpha between 0 and 1? X to the alpha?
Yes, okay. I mean, I don't want to answer this because this is more or less part of the homework. But so, but let's prove this part, this lemma. So proof. Well, if A is unital, then of course we can do something like this. We can consider y minus a to the minus half be a to the minus half. Let's take a to the minus half on both sides. This will be something like this. And this is, of course, this is what I want to know. This is a minus b, right? Now this is positive. So by what I mentioned before, by this claim, this has to be positive too. So, right? This is such a job. So let's start with this guy. And clearly A inverse is positive, right? Because think of the spectrum. Then we know that one which is greater than A inverse B, A inverse A to the minus half is equal to A to the minus half, B half, B to the half, A to the minus half. Okay, just maybe I should just let you know what is my goal. My goal is somehow to replace the role here of B and A. I want it to be B to the minus half, A to something like this, so I'll be able to multiply. Right, this is what I want to show. So right now it is just like writing A is greater than or equal to B, but I want to write something that will be like B inverse is greater than or equal to A inverse. So think about this equality, but write it as 1 is greater than b to the minus half, sorry, b to the half, a inverse b to the half, and I want to go there. Okay, you will see it in a minute. So this is nothing but just trying write b to the half, a to the minus half, star b to the half, a to the minus half. So we see that this positive element, I mean, this is a positive element which is less than 1 and greater than 0, so it is between 1 and 0. So, we'll think about its spectrum. So we know that, right? So we know that, about these elements, doesn't matter, that b to the half, a to the minus half is less than or equal to 1. Therefore, I can write it a to the minus half, b to the half is less than or equal to 1. And now I can write it like this. So 1 is greater than a to the minus half, b to the half, star a to the minus half, b to the half. And this is exactly what I want. This is b to the half, a to the minus 1. I think this is also greater than or equal to 0. So this tells us that b to the minus 1 is greater than a to the minus 1. Okay, so again, the trick here was just to, I used the fact that, right, that if you want the spectrum, I mean, I could have written this, maybe it's easier to see it like this. The spectrum of this guy, I'm changing it a little bit. I mean, it's just saying the same thing in different words. Maybe it would be easier to read it this way. The spectrum of this guy is in 0, 1. Hence the spectrum of this guy, right? Because they share the same spectrum up to 0. Okay.
You said share the same spectrum up to what?
Up to 0. So we proved that a certain thing in the first lecture, that the spectrum of AB is equal to the spectrum of BA. Maybe there will be problem with 0. Maybe you should add 0 to both. We gave an example where you should. But here it doesn't. Another thing that I want, okay, so right, I mentioned before things that work and don't work with applying functions on positive elements. One thing that also doesn't work is taking maximum. I don't have an easy way to take a maximum between two elements. So if I have a two element, positive elements A and B, I want to find an element C that will be sort of the maximum of them. I can do it in general. And by the way, what if one is in A? Of course, if one is not in A, do it in the utilization of A. So maybe I'll just add it. If not, if one is not working.
They are not really invertible if one is not in A. So.
You're right. I assume that one is in A. So sorry. Yes, it makes sense. Thank you. But of course, okay. So, but what I'm going to okay. So I want to write some claim and then explain that there is a huge difference between the unitary and non-unitary. Okay. So suppose that I have two positive elements. And let's assume also that they are no less than 1. In the unit ball. Then, or strictly less. Then I can find another positive element that will be with norm less than 1, such that A is that is greater both than A and than B. And I'm saying that for unit and sister algebra, there is nothing to show you. Why? Because we can always take C to B.
1.
No, so it needs to be strictly less than 1, so there is still a point, but
1
minus 1 over n.
1 minus x times 1.
I mean, yes, it can be the maximum of the norm of A and B times 1. So if A is unital, take C to be the maximum in the norm, say times. Do you see why the norm of A times 1 is greater than A? Think about the spectrum. If not, then I can explain.
Greater than
Greater than. Okay, so to prove, and of course, think about the non-unital case. So now you can do it. I think you can do what I'm going to say also about the unital case. And so the thing is that I'm going to build some kind of a maximum in a very artificial way. Okay, I'm going to construct something that would be. It's not going to be a maximum in any sense, but it's going to be some kind of something that will be bigger than both of them, and you will see what it means. So set f of t to be the function t over 1 minus t, t is in 0, 1. G of t to be t over 1 plus t. The point here is that the composition of f and g is t. Okay. You will see why this is important. Then f of g of t is check this if you want. Oh no, this is true, but I'm going to use the in fact the g of f. Although both compositions give me the identity function. Let y to be f of a plus f of b, and c to be g of y. So now let's see. So first let's check that indeed C satisfy the fact that it is positive and with norm less than 1. Well, why is C positive? Because f of a is positive and f of b is positive. So y is positive. So g is positive. This function takes, positive to positive elements to positive, right? But in fact, right g in fact maps the real numbers to the interval 0, 1. right? Check me. Right? So in fact, we show that C is positive and with a spectrum that is bounded by 1. So it is between 0 and 1 strictly. So since G of R is 0, 1,
it can be negative.
Not for positive inputs.
I'll close, sorry. You're right. Like this. So I put the positive element inside it. And yes, and no, I need another thing. And without 1, right? Because I have a minus something positive. So that's the picture. So it is without 1. So it means that the spectrum of C lies strictly here. So C has to be positive with norm less than 1. Fine. Now we need to see that C is greater than both A and B. So, okay. So clearly, f of A. Now, f of A has to be less than or equal to f of A plus f of B, I think. But f of B is positive. But now apply, but G is monotone, right? G is yes, okay, so I need to be careful. I'm going to use now the right, I mean, I said that you don't all, okay, what I want to do, I want to use the fact that G is monotone and to write something like, so G of f of A is less than G of f of A plus f of B. This is exactly C, and this is exactly A. So A is less than or equal to C, and similarly, B is less than or equal to C. But I remind you, you can do this. You can take a monotone function and apply it on some part of the spectrum where things should be reasonable, because we know that it doesn't in general. But here I'm going to use only the thing in monotone things that does work, that it is taking inverses. So, okay, so let's do it carefully now. So f of A is less than this. Thus, let's call this x for a second. Let's call this y. Okay. I call this y before. That's why I'm current with myself. So 1 plus x is less than or equal to 1 plus y. And now they are bounded away from 0, so they are invertible. And they are invertible by the claim 1 plus
x. You said we're in the non-use.
Again, work in A plus for a second. In the
performed work, if we say work in A plus.
No, because here you end up with C that is dependent on this one. Now I'm going to end up with an element that is not going to be dependent. I mean, this element belongs to A, but I mean, I'm applying A plus only for computations. This is fine. So now 1 is greater than 1 plus y inverse. This is by the claim. So therefore 1 minus 1 plus x inverse is less than or equal to 1 minus 1 plus y inverse. And therefore, this is g of x is less than g of y. And this is exactly what I want. This is the Okay, so this is what I wanted, but I needed to take care of the fact that I'm going to use functions that behave nicely in the sense of being one-to-one. So taking inverse is fine, but square, for example, is not.
Right.
Okay.
Did you say why C is in A?
G is a continuous function.
A is not unital. And
Well, use this. I mean,
continuous.
You're saying that we use continuous function. Yes. Okay. I didn't mean. Okay. I see. So what Alon says is that I defined continuous functional calculus only in the unital case. Okay, this is very good. So great. So this will happen here and then once in a while that I will not do something in a non-unital case, but then I will use it in the unital case, and then it will be a good time to do some kind of an exercise. If
We don't need it here just because t is between 0 and 1. So t over 1 plus t is the sum of minus t to the n. It converges because
you're saying I could have defined it
without using 1.
without using 1.
Like, yeah, you mean you explicitly say what is the power series and you don't see the constant term.
Yeah, there was some power series.
Very nice idea. Very nice, very good idea. But I will use this opportunity to remind something that I probably should have as before. So if C star, so if I is normal, and we know that C star of 1 and A is a continuous function over the spectrum of A. Then we can do continuous functional calculus. That suppose that C star of A is non-unital. So I think that I did define a spectrum of an element in a non-unital C star algebra. It would be its spectrum in the 1 point compactification, in the 1 point unitization, And I said that it doesn't matter if somebody else comes and define it to be the inverse, the spectrum like in a bigger unitization, because due to the permanence of the spectrum, we don't care. It will be the same spectrum. I mean, there isn't another way to define it. So there is a notion of a spectrum in case of a non-unital C star algebra, but then the spectrum might be not compact. So spectrum of A, well, what do I mean by that? No, it has to be compact inside the 1 point unitization. Okay, so what I want to claim is that show that C star of A is equal to the continuous function vanishing at infinity on the spectrum of A minus
Zero.
then you're allowed to do continuous functional calculus. Okay.
Hi, any C-star algebra that contains C-star of A factor through the unitization? Or
Yes. Okay. Also, we have Shivi's idea, which is really good, but so we can do it without using the one by working with series instead of that's good. But
why would, like, if you would tell me ask me how to do a functional calculus on a non-unital, I would just say it's functions vanishing at infinity, and then
Yes.
you can apply them.
yes.
So what was the point of what you just like, why would there be a problem to do functional calculus?
There isn't a problem. We didn't mention it before. We mentioned functional calculus only
I mean,
for a unital case because I didn't mention this.
So are you saying that the problem with the spectrum of A in the non-unital case is just it can be unbounded, right? Still will be closed, but
No, it will be unbound. This will be compact, but I'm going to remove a point for me. So now it is just a locally compact space. Okay? So think about it. Okay? So this is a good exercise too. Okay. Now
In the continuous functional calculus, you can only use a function for decay.
yes, in this point. So the dimension 0.
The same does not saying like take the power series and just first element.
Yes, but in continuous functional calculus, it's more than power series. That's the point, right? Because okay, there is this notion, I don't do it here because it's not a functional calculus course, but there's the notion of analytic or holomorphic functional calculus. This is something you can do in any Banach algebra. You can, I mean, if I give you a power series, well, you know how to define the thing. If it converges, define it, put it inside the power series. Convert. Also, there is a way to do it with Cauchy integral form, like holomorphic functional calculus. But we have continuous functional calculus, which is much better. It's for any continuous function, and which is of course more than just. Okay. So why did I do this? The claim, because I wanted to give you the next definition and to prove something. So this is again something that, okay, maybe I will write it and then explain. An approximate identity, or approximate unit of the C-star algebra is a net of positive contractions By the way, did I ever use the notion of contraction in this course? Running norm less than or equal to 1. And I know E lambda, net E lambda, such that if, I mean, it is increasing, if lambda is greater than mu, then E lambda is greater than E mu. And for every A in A, the limit of E lambda A is the limit of A lambda, which is the A. For the same limit, I mean, well, don't need to put it here. Now, the thing is that as I mentioned before, sometimes I prove things on unital sister algebras without caring too much about the non-unital case. And with the GNS, so at this point you don't know what, you don't suppose that, I don't assume that you know what is GNS, but the GNS is the theorem that we're going to prove next time. There was a point, I mean, it was very crucial to consider the non-unital case, and they did it with approximate identity. This was Segal part. So the GNS is a theorem that's called Gelfand-Naiman. Segal, when Segal did the non-unital part, so this will help us during this part of next week. Before that, it will also help us to correct something I did wrong. I told you that was not wrong, but unjustified last week. Oh, not wait. So now, a theorem. Any sister algebra has an approximate identity. By the way, if the sister algebra is unital, who can be our approximate identity? One. Seriously. Okay, so proof. So I'm going to take as my directed set of indices, indexes, whatever, to be the set of all these positive elements with norm less than 1 that we had before. And in fact, before we proved that this set is directed. So let lambda be the set of all A in A is positive, and as norm which is less than 1. By the previous claim, it is directed. So directed set is a set where for any two elements I can find third guy that will be bigger than these two. Of course, with respect to this order. Usually. So are you all familiar with nets? I mean, or is it something that I need to? You don't know about nets? So it's a good opportunity to read about nets. But let me just say, you can think of it as kind of generalization of sequences if you want, but it's a bit more than that. So when I say more than that, I mean, it's not that you converge in one direction. Somehow you can converge through some kind of weird partial order. But still, the set of indices has to be directed in the sense that any two elements has an element that is bigger than one. Okay, and if somebody is not familiar with the notion of nets, please go and read about it, because we're going to use them here and there. And Okay. So it is directed. Suppose that A is in X. Okay, so let's decide that for this theorem, I will call an element of the C-star algebra. I will denote it by X. And A will be the names of the elements of the C-star algebra where I think of them as an elements of the dice. Let's try. Suppose X is in A. Without the use of generality, assume that its norm is 1 or less than 1 or less than or equal to 1. Let epsilon be greater than 0. I want to find. We need to find A1 in lambda such that for every b greater than A1, x minus bx is less than epsilon, and A2 in lambda such that for every b greater than A2, x minus xb is less than epsilon, right? This will show that the net converges to that the net bx, ax, or xa converges to x, where a runs over this set. Okay. Cool. So let's do it. So note. So let AB be in lambda for a second. B with a less than or equal to b. Then, so this A is going to be in a minute this A1 or this A2. Okay? It's going to be this A. Bless you. So x minus bx squared, which is clearly by the C-star identity, this is x minus bx star x minus bx. Right, this is just x star x. Well, let me write it like this. Let me walk for a second. Again, I'm going to walk in the unitization. So this will be x star 1 minus b star 1 minus b x. But b is positive, so I can remove the star. Yeah. Right? So even I can write this x. But now but clearly right, but 1 minus b is greater than 0 and is less than or equal to 1. So therefore 1 minus b square will be less than 1 minus b, and therefore x star 1 minus b square x will be less than x star 1 minus b x. And this will be, since a is less than or equal to b, this will be less than x star 1 minus a x. So this is just a weird computation, but the point is that this shows that x minus bx squared is less than, well, right, we show that it is this guy. It is equal to this guy, x star 1 minus b x, but this is less than this. And this is less than, and this is just x star less than x star times x minus a. And this is less than 1. So it's less than x minus a. Okay, this was everything I wanted to show in here. I just wanted to note that if a is less than b, then x minus bx, or x minus bx squared, I don't care, is less than x minus ax. So if, and similarly, maybe I should write similarly, and x minus xb squared will be less than x minus a. So if x minus a1x is less than epsilon squared, then this will be less than epsilon, right? Then for every b greater than a1, x minus bx will be greater than epsilon, right? And this is what I wanted to show. I wanted to find a1 such that this will happen, and same for a2, right? So if I find a1 that satisfies this, so if for some a1 in lambda, I have this, then that, and same for a2, right? And similarly for so all I need to do now is to show you that I can find a1 in lambda, so it needs to be this kind. I need to show that I can find a1 in lambda that will satisfy this. Then I'm done. Then I know that for any b greater than it, I will have this, which will mean that they are. So I'm going to erase this. So do you have a question on the first part of the proof? I mean, on the explanation how I reduce the case on just finding an element that will satisfy this. This would show automatically.
You want something of the form, like an appropriate power of the absolute value of x would be a1.
So you're saying to take a1 to be what again?
Some appropriate exponent of the absolute value of x.
And then what?
Then, like, it won't change x too much at least.
Okay, I'm going to do some kind of trick like that. I'm going to find an a1 that will be some kind of a function of x and will not change the x too much. But
you say it's not like a discussion of.
No. Okay. But maybe there is a way to do it like this. I mean, this is a good idea. Case one, I'm going to divide it into case one where x is positive, and then for general x. So if x is positive, set a1 to be the following thing. So right, I assume that the x, its spectrum is between 0 and 1, right? So the spectrum of x is somewhere here. Now, take here 1, and here we have 1 minus epsilon squared. And here we also have epsilon squared. So I want to take this function. So this is going to be my f of x, my f of lambda. Okay, this is f of lambda. So I'm going to take a1 to be f of x. So let's check that it does the job. First of all, of course, it is positive, and of course, it is of norm less than 1, strictly less than 1, right? So a1 is greater than or equal to 0, and the norm of a1 is clearly strictly less than 1. So a1 is in lambda. Now I want to check this condition. So what is this? X minus a1x, which is nothing but x minus f of x, which is nothing but the supremum over the spectrum of x of lambda minus f lambda lambda, which is nothing but the supremum of lambda times 1 minus f lambda. You see, lambda is less than 1. 1 minus f of lambda is less than epsilon square. So this is less than epsilon square. So this is the response. And similarly, for A2, find A2. Case 2.
All the time we're assuming x is if x is greater than 0. Sorry. Yeah.
Yes, case 1 was we always assume that x is in the unit body. So I always assume that its norm is less than or equal to 1. This was without the rules of generality. If you prove the convergence on things that with norm 1, you're done. But here I assume that x is greater than or equal to 0. Case 2, x is general. X is general. So I'm going to do, the usual trick. It sometimes works, and it works better here. X minus ax square or a1. Or let me write it a. It's not going to be my a1 exactly. So this is what? This is x minus ax star x minus ax. This is the C-star identity. This is right. This is x star x. Well, let me write it like this. Let me write it like this. Again, I'm going to work for a second in the unitization. So this is 1 minus a star x star x 1 minus a. Well, probably I wrote it there. Let me write it there. What? I mean, I assume that I wanted to write here. This is x minus 8x. So okay, right, this is also true. I think this is what I want. Let me check for a second. I don't copy it. This is yes, so this is 1 minus a x star 1 minus a star. No. Yes, this is what I wanted. Okay. But this is just less than or equal to 1 minus a.
The x star we show twice, right?
What?
Don't you mean the x star we show twice?
I just okay. Maybe let me. I just want to write this x star minus a x star, and then we know that x star is positive, so this takes us to case 1. But maybe we need to take epsilon to be epsilon to the 4 because I have a square. So for this to be less than or equal to epsilon, I need this to be less than or equal to epsilon to the 4. So and go to this. Fine. Is the reason I got confused is for some reason in my notes, instead of writing case 2 for x minus ax, I did it for x minus xa, which is the other case. Similar for I mean, you have to prove it 2 things. One that you can find a1 such that this will happen, and same thing for that. When you walk in this direction, so here you need to take this star that, and I mean it's easy. You can see it. Okay. Cool. So now we know that any C-star algebra have an approximate identity. So this is a very fruitful I don't know, machinery. And maybe just let me mention something. Exercise again. If A is separable. Separable meaning that? Countable dense set, subset. If A is separable, then it has an approximate identity. Which is a sequence, and then TD, which is a sequence. This is not a super easy exercise. I mean, if you give yourself a small for baseball, if you're going to solve it, then
Funny thing is that there's another proof of this theorem, right?
what?
That there exists a like building a net, so which is a approximate unit,
Yes.
but that other proof like has a more direct translation.
So what is the other proof? Tell me.
Maybe I'll look it up later. Like it's more like constructive kind of building.
More constructive instead of running over all.
Yeah, you would
positive
take a
elements.
dense subset and then you can build like certain sums of
Yes,
squares.
you can do it. Okay. So this is more or less the essence of the proof. This exercise. What is that? Yes. Sure. Okay. And the corollary from not from the exercise, from the theorem, that is always also worth to mention. Every finite dimensional C-star algebra, every finite dimensional is unique. Why? Because what?
Compactness of the unit.
Compactness of the unit also.
So if you have an
Approximate identity.
it will have a limit.
And the
And then you
limit
need
has
to
to
claim
be
the
the
limit.
unit. So the unit ball is compact. So any approximate identity will have the subnet merging to some P. Obviously, this A would have to satisfy this, right? Could be one. But here is something quite important to claim. Every closed ideal, well, every ideal in our language, of a sister algebra is automatically star invariant. Hence, a sister survival. So, well,
Ideal means two-sided ideal?
yes. Well, ideal is always two-sided. Okay?
Mhm.
This is cool. I mean, you take this property of being ideal, and then automatically you get something that is star invariant. Okay, let's see why. So let J be an ideal. And let B be J intersection with J star. With a J star, well, by J star I mean, of course, all the A stars of AJ. Okay, so B is the intersection of two closed subalgebras in particular. So it is a closed subalgebra, but it is star invariant. So it is a C-star subalgebra. So B is a C-star subalgebra. Typically, B will not be unital, of course, because if B is unital, then J contains one. And then, since it is ideal, it is everything. It says nothing, right? So usually it would be non-unital. So our theorem is meaningful. So by the theorem, we can find E lambda in B be approximate identity.
It would be unital, right? It's just not the same unit.
Yes, it could be.
But then in the big one, there will be the same unit, no? Because when
No, because
No,
it satisfies less. It's
no, it can be unital. It can be unital. It might be unital.
or just functions on 0, 1, and then functions vanish on 0, half, and vanishing. No, it doesn't. I don't know, just.
Okay, let's think about it in.
No, it's true.
No, you had, I mean, you might have.
Like sub algebra, which is.
I always might have, I mean, it's easy to give an example for a subalgebra of a sister subalgebra, of a sister algebra, which does not contain the unit of the bigger one and contains the unit of its own. This is really easy. Take a corner of think about 2 by 2 matrices, then take the embedding of C in the left upper coordinate, and of course it is unitary, the complex numbers. But when you think of it inside the 2 by 2 matrices, it does not have the unit that comes from the 2 by 2 matrices. And I mean, typically, of course. But I don't care. At this point, I don't care about it. I'm just saying, let E lambda be an approximate identity. Be an approximate identity. Then if A is in J, then clearly A star E lambda is in J2 because E lambda is in J, because E lambda is in B. J is an ID, right? So what? Yes. So A star minus A star E lambda, which is A minus E lambda A minus E lambda. And
Can't you just say that the limit is
Yeah,
is the
the closer
definition of
you-
approximate identity
It's
that the limit of this, the limit of A star E lambda isn't it A star? By definition?
The problem is that A star is not in B.
A star.
It's a product.
No, but
No, no.
what I know about approximate identity, I know that for any element in B,
Yeah.
I have this convergence. But don't worry, we're going to fix it. I mean, it will take 1 minute. So I want to show that this goes to 0, right? If I show that this goes to 0, then indeed this will tell me that A star is the limit of A star lambda, therefore it is in J. Okay. This is nothing but this thing that I'm writing here. A star. Yeah. This is just a fancy way of writing the C star identity. This is not a fancy way, the usual way. Just open everything very naively. Now I'm going to use the triangle inequality, take the first part, which is A star minus A star lambda, and then take the second part and take also E lambda outside, and I have this guy. But the thing is, this is of course less than or equal to 1. So this whole thing is less than or equal to 2 times A star minus A star E lambda. But now I can do what you just mentioned, because A star is well, A is in J, so A star is in J. On the other end, A star, because A star is in J star, this is in J star. So A star is in B. So this goes to 0. and the last term. Along the net, so A star is in J. Okay. Okay. Cool. So now we know that being an ideal of a sister algebra means that you are closed under star. Now, last time I mentioned something like I told you, well, we discussed about star homomorphisms, and I will show that any injective star homomorphism is automatically isometric. And then I said, okay, so if I give you a closed star invariant ideal, we didn't know that closed ideals are star invariants then, but if I give you a closed star invariant ideal, then I can take the quotient and the map factors through the quotient to its image, which is true. But the thing is that what I forget to show is that the quotient is in fact a sister algebra. Well, it has everything. It has all ingredients. It is. Then I assume it is star invariant. It's closed. It's closed because it's a quotient of closed things. But what I didn't show is that it satisfies the sister identity, which is not immediate. And I forget it. So let me. I mean, this is a correction. Last time. Bless you. Also with some addition, because now I'm not going to assume invariance, star invariance. So claim. So it's more than that. And it's also not a correction, a justification. I said something true, but justification. I just didn't justify it. A claim A mod J is a sister algebra for any closed ideal J. Proof. Well, clearly we have everything. It's closed. We have the norm. We have the fact that it is star invariant. We only need to show. We only need to show the star identity. Quick lemma that also I think I will maybe leave you as an exercise. If I have the quotient map, like this map Q that takes me from A to A mod J, and then the norm in the quotient is equal to the limit along the approximate identity of that, where E lambda is approximate identity. Proof. So proof of the lemma, one direction is of course immediate.
Approximate identity in J, right?
Of J. So one direction is immediate because if E lambda is in J, then this is in J. And then by definition of the norm of a quotient of Banach space, the norm of the quotient is the supreme, the infimum over everything like this, so it is less than that. So this is by definition of the norm of the quotient by definition of the norm of the quotient. And this is an easy exercise, okay? Easy. Using this lemma, so I continue to prove this proof. We know that this QA star QA, right, in A of J, which is Q of A star A in A of J. By the lemma, this is by the lemma. Limit lambda of A star A minus A star A E lambda. In other words, this is the limit of A star A, 1 minus E lambda, working limitization if needed. When you compute things, feel free to do it. This is greater than the limit of 1 minus E lambda, A star A, 1 minus E lambda, because I only added here this term, which go the other way around. Do it carefully with the limits. This would be just nothing but the limit of A 1 minus E lambda square, which is right. The limit of lambda A minus A lambda, which is again by the same lemma. That's you. Okay, so this part was not, I mean, it's not hard, it's not difficult, it's kind of immediate, but it's not fully trivial. Because last time I said, the quotient is a sister. No. We do need to take care of the fact that the sister identity holds, but yeah. Okay, here I just used twice I mean, I used here, not twice, once the sister identity in A. So we'll soon take a break, but just before that, let me now write it correctly. We have given here corollary. If phi from A to B is star homomorphism, is star, then phi of A is a sister orthogonal. And the reason is that because we can factor it through the quotient, right? And well, we explained it last time. The only thing we didn't verify is that A mod J is indeed the sister algebra. But once it is, you have here a map that is right. If this is your phi, this is phi twiddle. This will be 1-to-1 automatically. It will be isometric. Therefore, it will be an isomorphism into its image. But it's an isomorphism of sister algebras. This was the missing part. So now it's taken. לא, הפכנו את זה
When should we come back?
הפכנו את זה יותר חדש. לא יודע אם זה יותר חדש. הפכנו שכל העסקה חד-חדתית היא דומה. פה השתמשתי בזה. וזה שהתקנה הזאת היא גיאומטריה, אז זה אומר ש-A או J,
אוקיי, ואז הוא
ודרך תקבל, כן.
יש לי שאלה. יש לנו
הוכחנו למעשה משהו קצת כזה, הוכחנו שהספקטרום של פי של A על הספקטרום של A, לדרך הרביעית של דיפרנציאלי. אז סתם הוא מוריד לוקח ספקטרום ומקטין אותו. בפרט, לדברים נורמליים, זה יגיד שברדיוס הספקטרלי מקטין אותם, ולדברים שהם לא נורמליים, בסיס על ידי ניתוס.
אם אנחנו אמרנו שאין
נורמלי. אז A קטן מביח שדברים בהקשר הזה.
אוקיי, זה אומר שהיא פתר.
זה אומר שהיא פתר.
זה בפרט A.
כאילו
אין...
לא, אני יכול להגיד שזה פתר חיובי, אבל בהקשר הזה.
אחרת זה לא תהיה נורא שליטי.
נכון. אבל בהקשר הזה, זה מה שאתה אומר, זה נכון. יש לחשוב על ספקטרום. אז מה נסתכל? ספקטרום, אז אני יודע שהספקטרום של... הספקטרום של B פחות A הוא... הספקטרום של B. אוקיי, יש את הספקטרום של A ויש את הספקטרום של B, וזה לא קשה להראות שהספקטרום של B פחות A שלו. בגלל שהספקטרום של B פחות A חיובי, אז זה מגיע בדיוק עד איזושהי, כלומר...
החצי, אבל פחות A.
כן, בדיוק. אז זהו, אז עכשיו זה דברים שנפרק נורמלי. אז הרדיוס הספקטרלי שלהם זה הנורמות שלהם. אוקיי, אולי של המינוס, אבל פה כל חיובי.
זה שווה בעצם.
זה ממש שווה לראשי. זה ממש שווה לראשי.
סתם ראשי.
כן, אז... אז אוקיי, יש כמה בחינות שלו. והייתי אומר ככה, הייתי עושה את זה בשלוש. אוקיי, נעשה את זה בשלוש. אז תסכים איתי ש... לא, אני רוצה להגיד ככה. אני רוצה להגיד כל פעם אוקיי? תסכים איתי שבי קטן שווה. זה ברור, זה כי זה אספקט. כן, וזה, אם אתה רוצה לפונקציה x, על אספקט. כך לפונקציה x, כשאתה חושב עליה, על הספקטרום של b, אז מצד אחד אנחנו יודעים שהיא שווה ל-b, מצד שני היא חייבת להיות קטנה שווה, הפונקציה הזאת. מה שזה f של כן. מצד אחד היא שווה ל-b, זה קלקוס.
אתם רוצים לסגור אותו ריקורדינג?
אני אף פעם לא סוגר, כי אז אני שופך מהקליפ. ניסיון עבר. לא, אז זה כמובן קטן לא שווה מהמקסימום של הדבר הזה, נכון? זה השאלה של הסופרמום של העמדה בספקטרום של הסנקציה הזאת, זה בוודאי קטן. הוא שווה במקרה של סלף אג'וינט שווה.
אם בי זה ספקט.
זה שווה כן. טוב, מה שאני אומר,
קיבלנו את התמונה הפונקציה, שזה גם שווה ספקט.
אני אומר שזה בי, יותר פשוט. אני אומר, להראות שזה גדול שזה יותר פשוט. אבל בוא תסכים כדי, בגלל שנגיד שאתה מסכים שבי וגם שאני מסכים של עצמו.
זה עם הרזולבנט אפשר
עם הרזולבנט. נגיד אתה יודע את זה, אז אתה צודק, אבל בפועל עד שהייתי משהו. אז יותר מזה, אני יודע אפילו לשם, ספקטרום של הוא מוכן, כאילו ב-B, כאילו ב-0. אבל הספקטרום של A, אבל נראה לי ספקטרלי ווי, מה אתה אומר? ש-A קטן של A. אוקיי, אז it goes down to show שבכל דבר קטן של זה נובע מדברים שעל אז כן, אז הנה, באתי להגיד לך משהו ממש פשוט, חזרנו. הפונקציה X. לא, אני אומר,
הנורמה של 1 1.
כן. זה לא עם X, עם X קטן שלה מ-1, אז 1 פחות X, בגלל שאני אומר, זה פחות מה שנדבר.
אוקיי, אז אני יודע מה איש קטן של X, נורמה של X היא קטן שלה מ-1. אם A זה פשוט 1.
אני רוצה להגיד כזה דבר, הפונקציה הזאת, הפונקציה B, זה לא קשה לעבוד, שהיא על הספקטרום של B, גבוהה שלנו. למה? בוא נצייר ככה. אולי הספקטרום נגמר פה, לכאורה, אבל עדיין, היא חיובית. אז הספקטרום גדולה שלנו מאפס. אז בפרט אומר שאף שלנו זה לא שונה.
אוקיי, הספקטרום בלי קטן שאתם יודעים שזה גם כאן.
כן, לא, B הוא סלף ג'וינט, זה אומר שהרמת ספקטרל שווה לרמת.
אבל באופן כללי, מה אישית?
האיש של הרבה קטן שלו.
זה עם הרעש ספקטרלי קטן.
כן,
זה תמיד נכון.
נכון, זה תמיד. אבל אם הוא לא היה סלף ג'וינט, הייתי יכול להשוות בינו ובין נורמה שלו. ובשביל שאני אגיד שהוא בעצמו כאיבר פוזיטיבי קטן של נורמה שלו, הייתי צריך לדעת שהוא פוזיטיבי. אז זה נכון תמיד?
כן.
שהרדיוס הספקטרלי של X קטן שווה בשביל שאני אגיד X קטן שווה מהנורמה של X. כן.
חלק של האפרוקסימט אידנטיטי, צריך את הפונקציה הזאת כדי שהיא באפס, תחת לאפס, כדי שתוכל לעשות קונטינוס פונקציונל קלקולס גם בלי האידנטיטי.
אתה מדבר על G של T?
בגלל שם פונקציה כזאת שהיא באינטרוול קטן הלכה לאפס.
כן, חד משמעית, כן. בשביל ה... מטעמים של אלגברה. לא נשמע לי הגיוני. ברור שזה הומורפיזם של אלגברה. משמר סתם פיזי, זאת אומרת שאני אסתכל באופן אלגברי זה ברור. זה שהסיפור הזה יהיה חד ערכי, ברור זה, כן, שאתה גרעין די זה זה. once זה חד ערכי אנחנו נגיד שזה איזומטרית. אז יש לך איזומטריק, התמונה האיזומטרית היא יושבת בתוך בי. פעם שעברה, אמרתי זה בציג כוכב, זה נכון, לא הצדק, אמרתי שזה סתם אינוולנט, זכרתי שאנחנו יכולים להוכיח שזה סתם אינוולנט מבחינה, אבל שכחתי שכן צריך את העובדה של זה שהסיסטר אידנטית מתקיימת פה, היא לא לגמרי, זה נשמע לעבוד. זה גם סיפור, זה יותר שוויונים, אבל זה יכול. תמיד זאת העוצמה. שליטה בדינמיקה. בגלל זה הם צריכים לסמפל את כל זה פיאנו פורטה. זה יכול להיות חדש חזק. אז תקראו את זה בפיאנו.
בואו נחזור.
יש לך דברים מגניבים יותר גם.
טוב, מה שהוא גם גרוע, אין לך עוד פעם.
אתה חשבת על הטיעון של בן גוריון?
לא, אין לי דרך כלל בשמונה בבוקר, כאילו זה עבר בראש, אין לי דרך כלל בשמונה. תלך. טוב. רק בגלל ששאלו אותי על זה בהפסקה, since I was asked during the break about it, I will just verify that we're okay with this. The fact that, so verify you understand why if A is positive and it's less than B, then the norm of A is less than the norm of B. Okay, I mean this is something. I mean this follows immediately from the fact that a positive element is less than or equal to its norm. Why is this true? Okay, now I want to take a break and to speak about some weak topologies on B of H, the Watt and SOT topologies. So let's read. So
what sought topology on U of H. So so we have, of course, maybe okay, we have the norm topology, right? On U of H, which is the operator norm. We have the sought topology, strong operator topology. So it is generated by the subaces ut psi, which is all the s's such that t s minus t psi is less than 1. So this is just a subbase. If you want it to be an actual base, you need to take finite intersections of such. And it would be a basis. And in terms of nets, so the easiest once you verify this defines an honest two-guy topology, it's easy to understand this topology with nets. So T alpha converges in the strong operator topology T. If and only if T alpha of psi converges in the norm of the Hilbert space to T of psi for every psi. Okay. We also have the weak operator topology. Weak operator topology. What? That is generated by a subbase. Yes, so here I'm just running by before I was running over all T in U of H sine in H. Now I'm running overall T sine eta, all the S such that the inner product of eta S minus T sine is less than. Well, let's talk about it for a second. We didn't mention it yet in the course, I think. So, inner product for us, this is the linear part, and this is the linear part, and this is the anti-linear part. So, like a physicist. I mean, this has nothing to do with the topology. This is just with the notation of the inner product in our course. Okay? In our course, inner product over C, of course. So, I assume this part is the linear because I like to think about the left guys as the like functional setting. So, like physicists. It's not that important. So, in terms of nets. This is what you think it is in terms of nets. T alpha converges sought to T if and only T alpha psi is what next. What eta converges to every psi and D. Now, a quick question. Do you guys know what are trace class operators? Is there anyone here that doesn't know what a trace class operator is? Okay. Okay, let me ask a different question. Do you guys all know what is the spectral theory of a compact operator? How does the spectrum of a compact operator look like? I mean, something you must have seen in functional analysis at a certain point. That the spectrum of a compact operator is like a sequence, maybe, I mean, it is a countable set, maybe a sequence converging to zero, or just some finite set. So if it's a positive compact operator, then I again have a sequence that maybe converges to zero, or it's finite, and I can sum the element, and if they are summable, then they are positive elements. If I can sum them, then I call to such an operator a trace class operator. Okay, maybe I would give an exercise. Okay, maybe I'll write an exercise on this because I want to speak about okay. So I will just mention that there will be another topology that will be important for me, not for this part of the course, but for the second part of the course, operator algebras that are not necessarily self-adjoint, and this will be the weak star topology on B of H. So we can view B of H as a dual space is a Banach space, dual to these trace class operators. And then it has a new norm, a new topology, star topology, that I will need to use. So but maybe I will give you some exercise. Okay, never mind. Right now I just want to mention these two topologies, or three, including the operator. And of course, you can see that to check that if you go like this, then you have more open sets or less open sets. Right? More open sets. It's harder to converge. If something if a net converges here, then it clearly converges here, and it clearly converges here, because harder to converge when you have more open sets. Okay. Well, let's do some examples. When you know that n is a power variable space, you can think of it as if it was L2 of the natural numbers. So let's think about the L2 of the natural numbers, right? Just take an orthonormal basis and think of them as if they were delta sequences. And let C be, so if C is an element of the form x1, x2, etc., I define xi to be 0, x1, x2, etc. Sometimes called the unilateral shift. So it's easy to check. Easy to check. And that S star of psi is x2, x3, etc. So in particular, S star S is the identity. So S is isometry H. Now note that S star to the n So if I take such a vector psi and I act n times with star on it, then I push it to the left. In the SOT topology, this will converge to what? You want me to write bigger? I mean, you can move maybe here.
Zero,
Why?
because it is contractive and the mass is on the right side.
Right. So this will convert to zero, since what is the norm of S star to the n of psi square? It will be just the xi's square when I is greater than n or n plus 1, right? But this is just a tail of something that converges here, so it goes to zero. But so in particular, it also goes to zero in the water body. But clearly, S star of n doesn't go to zero in norm. Right? Two, S to the n itself goes in what topology to zero? Why?
No.
Because of one. Because eta S n of psi is nothing but S star to the n of eta psi. And if this goes SOT to zero, then Cauchy-Schwarz inequality tells us that this goes to zero. Right? So from Cauchy-Schwarz, this goes to zero. Cauchy-Schwarz plus 4. But Sn does not converge in SOT to zero, because the norm of this thing is exactly S is an isometry, but S to the n does not converge SOT. Right? Because S to the n of Ax is equal to the norm of it is equal to the norm of it. Okay. Let's discuss a little bit about continuity of operations. So I need a three-dimensional table now. We don't know how to do it. I want to have operation. Continuity. Okay. So, no, SOT, what, no, SOT, what, no, SOT, what, and maybe I need another one. Why aren't there three-dimensional tables in the world? So the first operation I would like to consider is the star operation. T goes to T star. So is this continuous in the norm topology? Well, it's a C star algebra, right? T star is equal to C. So this tells us that, well, it has to be convex, you know. What about sort topology? Can you give me an example of a sequence converging to zero? But when you apply star on it, it does not converge to zero.
SM star.
Right.
S star, one of them.
So S star, right? Okay, we know the formula. Yeah, the sequence converges to zero, but when you apply star on it, it is not. What? Of course, because of the structure of the word. Right, since eta t psi is equal to star is equal to t eta psi, which is in strong psi t eta something like this. So this tells us that if something converges, okay, yeah. So star is continuous. Next operation, right and left multiplication. So you fix A, an operator, and you consider right multiplication in A. And same for left multiplication. So is this continuously norm? Of course. In SOT, think about it for a moment. Of course, and also in, I mean, this is. But now what happens if I consider multiplication as a function from B of H times B of H to B of H. So TS goes to then in norm, where we know it is continuous, right? This is a Banach algebra. So the norm of TS is less than or equal to the norm of T times. In SOT, is it continuous? So take S star to the n as one of the sequences, and S to the n is the other sequence. S star to the n, S to the n will be 1. But this alone converges to 0. And the product is 1 constantly. So it is not. Right, so this is not. And we have example on the coming here. Right, S star to the n converges to 0. S n converges to 0. I mean, well, okay. Yes, I should say that it is bounded. Okay, maybe. Okay, so let me write it like this. This is for the what, maybe example. So for the what, S star to the n converges to 0, and S to the n converges to 0, but S star A to the n. I mean, but this is always equal to 1. Why yes. So
One doesn't converge.
yes, 1 does not converge to 0. But on SOT, so think how can you produce an example from this, more or less. Okay. So I mean, it's written here, more or less, but think about it. So you need to give me, I don't know, let's say 2 nets that converges to something, but the product doesn't converge to the product of the things. Okay. And in fact, I can say more than that. I can discuss about continuity. So another row in this table, I consider the function where you multiply. So this is the unit ball of B of H. This is B of H, and this map goes to B of H. So I have, again, ST goes to ST. I don't have a fixed S, but S is bounded by 1 in norm. Then in this case, I claim, so again, we have norm such what? That this operation is, of course, a continuous in norm, because the previous one continuous. It is not continuous in what? And it is not continuous in such. It is, yes, continuous. Okay. So this is exercise.
What is it? VHF1?
The unit ball of BH. Okay. So you should be careful when we speak about these topologies. When you take some kind of operation, be careful. Okay. Claim, which I will not prove, what and sort closures of convex sets coincides. Definition, the commutant of a set S in B of H is just a set of all S prime of all elements in B of H that commutes with S. Let me put it capital. Such that TS is equal to ST for every S. Okay? So that's the commutant. Think about it for a second. If two elements commute with S, then also the product commutes with S and their addition. So in particular, a commutant is always an algebra. And it's clearly closed under the what topology, and in particular under the sort and norm topology. Because, well, if you commute and take limit, you can think why you commute. And the limit has to commute also. Great. So this will always be a what closed algebra. And if S happens to be star invariant, then it will be in fact what closed C-star. Okay. So I note that if S is star invariant, S star is S prime is what closed. The algebra, C-star subalgebra of BOH. And it is always unital, by the way. Note that it is unital, right? Mm-hmm. The constants are unital. What's the letter? The letter is truly S. I don't know why. Sorry for that. Because I want to think of it as a subspace, perhaps. So theorem. So before theorem, and another remark, also clearly, if I take a set S and I take everything that commutes with everything that commutes with S, taking twice the commutant, then it must contain S. Because of course S commutes with everything that commutes with S. Right? So S is in the double commutant of S. And now, theorem that A in the unit of H, U of H, in U of H, be a sister algebra. Then double commutant is equal to its third closure, which is equal to its fourth closure. This is sometimes called von Neumann double commutant theorem. And so some of you come to the Midrasha, which is the one of the seminars here. And Michael gave a nice talk in the Midrasha last week when he proved this theorem very nicely. So I will not repeat the proof. Those of you who didn't see it can watch it online. I want to say if Michael permits, but it is. It's there. So you can go to the website of the Midrasha groups. I will not repeat the details. He did it really nice proof and go on. But this is, I mean, something you should be familiar. You should see it at least once. Go over it. There's a trick there which is really nice and it is worth to see at least once. And I do want you to see it, but I don't want to repeat because at least half of you saw it last week. And the others can read this or watch this. Okay, and the definition. If A is equal to one of these, right? They're all equal. Or a sister algebra is not that. A sister algebra. A sister algebra A. Subalgebra of group H. Sister subalgebra. A of B of H, such that it's called von Neumann algebra. Now, I'm not going to show it, but if you think about commutative, about sister algebra as a non-commutative analog of compact spaces or topological spaces, right? Because in the commutative case, there are exactly those sister algebras of continuous functions over a compact space. Von Neumann algebras are the non-commutative generalization of measure space. In fact, any commutative von Neumann algebra is L infinity of some space. Okay? Of course, it's also a sister algebra, so it's also C of something. It is unital, so it is continuous functions over an honest to God compact space vector. But that's fine. What else
Can you say why it's so clearly that S prime is what close?
exercise? I mean, take a limit and use the fact. So I'm just claiming that if every guy in the net commutes with S, then the limit has to commute with S. And this is something you can see inside in a product. So, so you do write it and there's nothing. Okay, so let me think if I want to say anything else about these guys. Okay, let me just say that there's something tricky here because I said that the Von-Neumann algebra is a sister subalgebra of B of H. So it comes with an H. So apparently, I mean, it seems that it's not something intrinsic. It's not that I take a sister algebra, that is some sister algebra, which is not in B of H, and I can say, listen, guys, this sister algebra is a Von-Neumann algebra. In this case, you must tell me, no, you can discuss about being Von-Neumann algebra. You have to give me an H. You have to put it in some B of H, and then maybe it's a Von-Neumann algebra, maybe it's not. Maybe it depends on H. Maybe I can put it, I can embed it in one B of H, and it will be a Von-Neumann algebra, and in another B of H, it won't be a Von-Neumann algebra. Of course, the answer is that no. There is the theory of Sakai, and he generalized this. So Sakai defined, he called a sister algebra a W star algebra. W for weak, I guess. If it is a sister algebra that is a Banach space, it is a dual space, some other Banach space. And then he showed that any such a sister algebra, any such W star algebra is a Von-Neumann algebra. I can represent it as inside B of H for some H in such a way that it will be Von-Neumann algebra. I think we're not going to discuss it further in this course, but there is something I do need from Von-Neumann algebra, or at least from certain word convergence. The thing is that sometimes when you have continuous functional calculus, it doesn't let you to produce things that are not continuous, right? So suppose I have some kind of, I don't know, think about a positive element. So I don't know, think about an element that's in 0, 1. Sometimes, next time, in fact, I will want to know things about the subspaces in which an operator acts, so I will want to connect between an operator into its range, say, or things like that. For that, I will need to turn the operator into a projection. And then I'll say, okay, I have a projection, I can project an Hilbert space onto something, this thing is a space, subspace. I will want to turn it into a projection in a way that, let's say, it will commute with the original operator. So I start with an operator T that is a spectrum between, positive spectrum between 0 and 1. And I will want to find a projection that will commute with T. So if T has a spectrum that looks like this, I have no problem. Why? I can take this function, f of t, right? It is a continuous function on the spectrum, and I'll be able to discuss about f of t, and it will be kind of easy to show that f of t, well, it is a projection, right? Because square on the spectrum, the square of it will be itself, and the star, and it's positive, so it's not so self-adjoint. But if for some reason the spectrum is not, I know, it has a full spectrum, say, then I won't be able to do it. I won't be able to take a continuous function and plug it in and say I get some kind of projection this way. I will be able to do it inside the Von-Neumann algebra generated by T, not inside the sister algebra generated by T. Okay, so I will want to do it. So now I will maybe write this lemma that I need. And let's prove it. So I just discussed vaguely what I wanted to do. But now here's something I will use So let me maybe erase this so we can start moving from here. Then P alpha is an increasing net of self-adjoint and operators. I think self-adjoint would be, I will need it in fact only for positive, but I think self-adjoint is also okay for me.
Because increasing you need like
Yes, and at the beginning when I defined the order, I said
you don't do both. You don't need
that usually I will use it for positive elements, but in fact I need just the difference to be positive. Okay, let's do it on positive. I mean, I will use it for positive operators, but maybe the proof will be true also for self-adjoint. Let's check it again. I think it should work also for self-adjoint. Yes, let's leave it. Increasing net of self-adjoint operators, then bounded from above. Then, when I say bounded above, I mean by some m in the range. Then, the sought limit of T alpha exists. So the limit in the strong operator topology exists. And there's a really nice trick to show it exists in the weak operator topology. Let's do it. So proof. So
in the weak operators because the unit ball is will stop.
no, I didn't say anything like this. But define psi comma eta to be the inner product, the limit along alpha, along the net of the inner product of psi and T alpha eta. So exercise. This is an increasing sequence numbers. So if you take eta to be psi, then these are all positive, right? Well, the fact that T alpha, oh, this is alpha joint. This is real. And this is an increasing sequence of real numbers because the differences are positive because T alpha is increasing. So this will tell us that, and it is bounded above. So it is a converging sequence of numbers. So this will tell us that this is a converging sequence of numbers. So we can take the limit of it.
For this one, so different side and
Yes, think about
Yes.
why. I mean, it's not hard to see it. Then this guy has to be a sesquilinear form. So this is sesquilinear, a bounded sesquilinear form, bound sesquilinear form. Something you know about sesquilinear form from linear algebra is that they're of the form inner product of psi with a matrix. But this is true also in B of H. Same proof works. I mean, if it is bounded, it's sesquilinear form. So, so there exists T in B of H such that psi times zeta is psi inner product with T theta. Show that T alpha converges to T. By the way, exists. Maybe it's worth to also note that I mean to also add in the theorem that I mean this is easy. It's made in particular. And T is alpha joint 2, and T is greater than or equal to T alpha. Of course. So just to put it in context, this is sort of you should think of it as sort of dominated convergence theorem. Okay.
This is only what you prove, right?
What?
What? Okay.
Yes, I now we need to make this sort. So let's make it so. This is an easy trick. Okay, so to make this sort, note that whenever whenever S is greater than 0, then S psi square, which is equal to S psi S psi. Be ready for the trick. This is equal to S. I'm going to take half of this S to here. So S to the 3 halves psi, S to the half psi. This is by Cauchy-Schwarz is less than S 3 halves times psi times S to the half psi right? And this what?
Square.
Y square? No. I think it's fine. This is less than S 3 halves times psi, or this is equal to, and this is S to the half psi, S to the half psi to the half. But this is nothing but less than by 3 halves psi and y psi S psi. Yeah. Right. Now plug in, instead of S, plug in T minus T alpha. So thus T minus T alpha xi square is less than T minus T alpha to the 3 halves psi T minus T alpha psi. Yeah, right? This is bounded by something called 2t to the 3 halves. This is bounded by psi, and this goes to 0 because they converge in what? So 0. This goes to. So this shows that in fact the alpha converges to T in the strong equation.
Did you show here that the what and SOT agree on bounded sets? Is this or not, or you use more?
No, I use more than that. I use the fact that they have increased. So for increasing in X, for
Where
increasing,
did you use the increasing to show that it's what convergent, but now in this
you're saying this argument
It's positive.
positivity,
I did use
that it's on positive boundary.
yes, this
that
is
it's
true
on
for positive.
positive. It's not true that Watten's not agreeing about its sets, right?
No, it's not true. It's what it's not. Okay. I think we have an example for that. Not today. I mean,
Yeah, they're SNS.
SNS are they're in the unit.
Yeah.
Okay. Good, I'm done with that. Now, a quick definition and a quick theorem. Okay, yes. So, definition. Star homomorphism. Homomorphism. Phi, let me call it phi, from A to B of H. It's called, it has a spatial name. If the range is B of H, it has a spatial name. It is called a star representation. It is irreducible if there are no closed subspaces K strictly contained in H and non-trivial space, such that pi of A K is in K. So such that, in other words, such that K is pi invariant. What? Pi of A invariant or pi invariant? Okay. We will discuss more about representations next week, but right now we can prove the following thing. So claim, or theorem, let phi from A to B of H be a star representation. Then phi is irreducible if and only if the commutant of pi of A is trivial. I mean, we always have in the commutant one of B of H, right? This one is one of B of H, okay? I don't write, I mean, of course, there is no other one can be. So we always, maybe I should write it C. This one. So if only the trivial element commutes with pi of A. Oops. So if pi is not, so now I'm showing this direction. If pi is not irreducible, there exists a K in H, non-trivial, such that pi A of K is in K. Let P in B of H be the projection, the orthogonal projection of onto K. Okay, so I take A and I project it onto its subspace K. I claim that P is in the commutant of A. Then for every psi in H and for every A in A, you see pi A of P of psi, this is in K. So this is equal to pi of T of pi A of P of psi. But on the other hand, so this is true for any psi in H, נכון? So pi A P is equal to P pi A P, but now do it to A star. So in particular, pi A star pi is equal to, I don't know why I call it phi. No, you know that I think in Greek they call this thing P, right? So, I had a really good friend who was Greek, and he used to be a postdoc in my department when I was a PhD student, and he used to give talks and on the blackboard, and always like he called the element P and phi, but with P it was funny. Also they write alpha like this, not like this. So okay. So by taking star on this, you see, you get pi, you get P of pi of A, equal P of pi. So, but this is pi. Right? And P is non-trivial projection. Okay, conversely, here I need this idea with spectral projection. So conversely, we move right this direction. Suppose there exists T that is not a multiple of the identity inside the commutant of A. So I can, of course, assume that T is positive. Why? Because well, I can take it into its self-adjoint parts. So we can write T as T1 plus I T2, and it's not hard to show that these guys has to be also in pi A prime. T1, right, is T plus T star, and right. So and then and one of them is not a multiple of the identity. This guy is not a multiple of the identity, and then I can add to it 1 times a lot to make it positive. Okay, so without the loss of generality, we may assume T is an operator greater than 0, and even I can make it with norm less than 1 by dividing it by its norm. So even norm exactly. Right, so let me just write in a nutshell what I explained. Decompose T into T plus T star over 2 minus I T minus T star over 2I. One of them is not constant. Otherwise, it is constant. Call it S. I mean, I don't know if S is this guy or that guy, but and then consider S tilde to be S plus the norm of S. This is strictly positive, right? Because if it had something negative in the spectrum, I shifted it to the right hand side and let S twiddle to be S twiddle divided. Okay. So now, for any alpha in 0, 1, you can define the function f and t, which is 0 when we're before alpha, and then it looks like t minus alpha to the 1 over 2 to the n. So this is when t, I'm finishing, it will take me a minute. Okay. This function is continuous. And note that Fn of t square is F n minus 1 of t. Thus, by the theorem from before, by the theorem, Fn of our t converges to some p sort, but due to this, p has to be a projection. So by the theorem, p is equal to p star, but as Fn t square is Fn minus 1 of t, we have to get that p square is p. So p is a projection. So p is an orthogonal projection and take range to p. Orthogonal projection. Let K be its range. Let K be P of H. The image of this. So I claim that that K is invariant. So K is phi A invariant. Invariant. Okay.
And K is not everything because alpha.
Yes. And P, yes, and P is not, and K is not everything because P is not real. Because I constructed this. Exactly. The thing is, I mean, the point here is that this P, well, it lies in, not in the C-star algebra generated by T in general. Again, if somehow T happens to have this spectrum that is discontinuous, then fine, I can do it inside the spectrum of the C-star algebra. But in general, I have to take here the what closure, or sort closure, or double comment.
Why is P self-adjoint?
I didn't say that it's self-adjoint. So you say that I need to what again?
Why is P self-adjoint?
Why is P self-adjoint? Because
The previous lemma.
because the T are self-adjoint positive or self-adjoint or whatever. By the previous lemma, Well, we didn't check it, but I wrote it that the limit will be also self-adjoint or positive, depending. Maybe. Okay. In fact, I think we used it. No, we didn't use it. We just used the fact that T will be bigger than T alpha. But in particular, the T alpha, I mean, well, if they are positive, then T is positive. The limit is positive. Okay, yes.
What is the role of alpha here?
Nothing, just pick an alpha. You mean that there is another alpha here? No.
I mean, in order for it not to be trivial for the
Yeah, you need.
for the projection to be not to a trivial subspace.
I need to pick an alpha. Yes, maybe.
It should separate the spectrum somehow. Right?
Yes, sorry, maybe I should have mentioned it. Yes, I mean, this is true for any alpha, and of course, I can pick an alpha that will separate the spectrum in a non-trivial way. So yeah, so this is true for any alpha, and for this to be non-trivial, so please don't talk about projection until you reflect. This is true, but maybe somehow it is invariant. But yes, just maybe let me mention this, and then we can go. Thank you. So for P to be non-trivial, to be not in this, we should pick alpha such that the spectrum of T intersection with 0 alpha is non-trivial, and the spectrum of the intersection with alpha 1. And we started with T, which is not constant. Thus, we can do it. Since T is not constant, spectrum is not single. Right. Okay. Thank you for the. That's the reason I wanted to. Great. So now we know that irreducible representations are exactly those representations that their commutant is non-trivial, and we'll continue next time. Bye.
All right.
Bye, Anton.